Hello everyone, today we're going to be learning about resting membrane potential and action potential. Have you guys ever really wondered how you tell your body to do certain tasks? For example, jumping jacks or even lifting some weights? Well, I'm here today to teach you how this happens and why it is so important in our everyday lives. First of all, let's start out with the basic anatomy of a neuron. A neuron is a cell of the nervous system specialized to generate and transmit electrical signals. Although they are only about 1 millimeter long, they are one of the most complex and important cells in the body. Each part of a neuron plays a key role in resting membrane and action potential. For example, we have many different key components of a neuron. This right here is called the cell body or soma. This is just the main part of the cell. And inside that cell, just like every other cell, we have the nucleus. Nucleus, like you guys know, plays a key role in making other cells and housing the genetic info. Right over here, these pink things are called dendrites. These important structures right here play a key role in receiving electrical inputs and basically just receiving messages to generate what we will learn about later in action potential. Right here is the axon, the little green thing. And what this does is, this is what the action potential generates down. It propagates right down it, all the way down to what are these, the axon terminals. These axon terminals secrete neurotransmitter, and in some cases it could be acetylcholine or norepinephrine, for example. These blue things right here are called Schwann cells. They're basically made up of a myelin sheath. What this myelin sheath does is it basically insulates the axon, allowing the action potential, once it gets generated, to move down it quicker. It propagates from each node of Ranvier, which are those things right there. The most important thing of a neuron or nerve cell is the axon hillock. This structure right here is what generates the action potential in every nerve cell. Resting membrane potential is a key component of all neurons in the body. Resting membrane potential is simply the displacement of ions across the inside and outside of the neuron. There are many different factors that affect resting membrane potential. For example, we have leakage channels. We have leakage channels that are permeable to different ions such as sodium and potassium. Another key component is the sodium-potassium pump. This is the sodium and potassium pump. This important transmembrane protein plays a key role in resting membrane potential. How this works is by pushing sodium and potassium against its concentration grade. All that means is sodium is going to have a higher concentration out here, and we're going to push it out there, and vice versa with potassium coming inside. There's going to be a lot in here, and we're still going to push it in here. For this pump to be activated, it requires one ATP molecule. This ATP molecule attaches on to the protein right here and is phosphorylated. Once this happens, this protein right here will change shape due to the fitting of the ATP right here, and what will happen is sodium will move against its gradient outside of the cell. At the same time, potassium is going to rush into this protein, and what happens with the ATP now is it's going to detach itself, and the protein is going to change shape again. It's going to make it look like this, and the potassium is going to move into the cell. This pump is so important in resting membrane potential because of leakage channels were the only transmembrane proteins in the neuron, and the concentration of sodium and potassium would equalize in the cell. We simply do not want this. Alright, so all resting membrane potential is the displacement of what we talked about, sodium and potassium on the inside and outside of the neuron, more specifically the axon of the neuron. If I were to voltage meter inside the cell, you will see that the displacement of the ions would equal a negative 70 millivolts, which basically means there are more sodium ions on the outside of the cell and less potassium ions on the inside of the cell. To put it simply, the inside of the cell is just less positive than the outside. And that's all the negative 70 millivolts is. It's not actually negative, it's just less positive. Yes. Now that we have an understanding on resting membrane potential, we can now get to the fun stuff. For example, how do you tell your body to move something, like your arm, or to lift a gallon of milk to just chug it in the morning, or simply to throw a baseball? There are a few things we need to know about how a neuron in your body creates or generates an action potential along the axon. What happens is, let's just say this neuron right here is also connected to another neuron, let's say over here. What happens is the other neuron over here is going to synapse with this neuron, just meaning it's going to communicate with it. It will send what is called a graded potential. This graded potential could be very minute, or it could be large enough to actually generate this action potential. This chart right here represents an action potential, let's just say at the beginning of the axon, given millivolts per unit time. So what's going to happen is you have your resting state right here, resting membrane potential at negative 70 millivolts. What's going to happen to generate an action potential is the communication or synapses between two neurons are going to start creating some graded potentials. Now, the more important thing to realize is this number right here, negative 55 millivolts. If any one of these graded potentials hit that threshold number of negative 55 millivolts, there will always be an action potential. What an action potential is just the depolarization and repolarization of the cell membrane of the neuron. What happens in depolarization is voltage-gated sodium channels are going to open and allow sodium to rush inside of the cell. Now this will happen and it will keep increasing the ions of sodium inside the cell, bumping up the millivoltage all the way up to 30 millivolts. That's your peak. That's as high as it goes. At that moment, those sodium channels close. Your potassium channels now take over. These guys open and potassium is going to flow out. Once potassium flows out, the millivoltage is going to decrease all the way down past negative 70. This is important too. This is called hyperpolarization, which means more potassium flows out than what should. So what happens is, this is where your sodium potassium pump and leakage channels comes into play. What they do is they just slowly and surely generate the ions and displace them across the membrane until it comes right back to negative 70 millivolts. We have a pretty good understanding of the action potential as seen on a graph right here, just going over the basics. We're going to get into the nitty-gritty and go into what happens at the membrane level of action potential. To start, guys, we're right here at the resting membrane potential. This is just the standard negative 70 millivolts right here. This is where we are on the graph. Okay, what happens is, as the graded potential hits threshold at negative 55 millivolts, this right here is going to transition over here. What's going to happen is these voltage gated sodium channels are going to open, like we have said right here, and sodium is going to rush into the cell very fast. This is going to cause the depolarization of the cell membrane, which means the millivoltage will increase to a positive 30 eventually. Once this happens, here you have your potassium channel, and it is going to be blocked still. Once it hits the positive 30, the peak we're going to go down here and we're going to repolarize the cell membrane. So what's going to happen is this ligand right here is going to block the sodium from coming in, and the potassium channel is going to open up, and what's going to happen is potassium is just going to fly right out. Once potassium flies out, it's going to quickly go right back down all the way. It's going to go a little past negative 70 millivolts. And what's going to happen is, due to this, the sodium and potassium pump and other channels, like leakage channels, are going to displace sodium and potassium very slightly over unit time until we get back to negative 70 millivolts. It just slowly, just by facilitated diffusion. And you know how the sodium and potassium pump works. Now that we have gone over resting membrane potential and action potential, we could piece it together and understand how we complete everyday tasks. Thank you for watching. I hope you guys learned a little bit about this video, and I hope it helps you out in the long run.